problem?
I think it had a CH2 with a CH3 over here.
That's what you gave us in class, but I just looked at the one online and that one was the one that had that.
Oh.
So I didn't know.
Which one to do?
Yeah, so I did that one.
Okay.
Me too.
Okay, then let's do this. Well, okay, fine. We'll do this one, and then I'll do the one with the ethyl group. I'll grade either one. It doesn't matter. But if you did one with the ethyl group, they are going to have two distinctly different major products. So we'll talk about both of them, but let's do the mechanism for this one. Okay, so what's the first step in the mechanism when we have an alkyl halide? My first step is going to be to break the carbon-halogen bond and give it to the chlorine. And so that's going to give me a carbocation. The transition state for that is, again, first step for transition states is going to be write a dotted line to the bond that's being broken or formed, which in this case I'm breaking the carbon-chlorine bond. And if you want to average the charges, you could certainly do that. Another way to look at this is to say, okay, wherever there's a plus charge or wherever there's a minus charge in the reactants and the products, that's where the delta plus and minus charges go in the transition state. So in other words, I could say, well, this carbon has a plus charge, a delta plus goes there, the chlorine has a minus, let's put a delta minus there. So in the transition state, it would look like that. And if you want, you can say chlorine 0, chlorine minus 1, average delta minus. But really, wherever there's a plus or minus charge, that's where the delta plus and the delta minus charges are going to go. So our first step in the generalized mechanism is going to be break the carbon-halogen bond to form the carbocation. That's the first step. Then the second step is going to be to lose a beta hydrogen. So what we can do is we can basically separate these out, if you'd like, and we can look at the mechanism for losing each of the beta hydrogens. You don't have to necessarily do one carbocation with different arrows. So we can do them one by one here. Somebody asked a question, if you could write the first step once and then just do the second step with each beta hydrogen individually, and yes, you can do that. I will have to say I had students sitting with me and they had to tell me what that question meant initially. They're like, I think it means this, and I go, okay, good thing you're here because it would have taken me a while to look at it from that perspective. And it wasn't the question that was wrong, it's just, it's a long day, and it's 1 o'clock. So let's do each one of these. What would be the second step? Second step is to break the carbon-hydrogen bond and put the pair of electrons there to form the double bond. Now, why is this happening? It's happening to basically form a double bond and get that carbocation back to neutral. That's the overall goal of that reaction. So then I'm going to have a transition state, and then my final product is going to be a CH2 plus an H plus. Okay. So we'll write the transition state, then we'll go back to the H plus and answer your question about what happens. So in the transition state, the only thing different about this transition state is, in this case, we're going to write a dotted line to the bond that gets broken, and we need to draw a dotted line to the bond that gets formed. So it's always the carbon that gets broken and formed. We always write those dotted lines. So this is the first, outside of SN2, this is the first mechanism where we've got a dotted line broken, a dotted line formed. Then again, charges, this H plus, that becomes an H plus, so it's delta positive. This carbon started out as a carbocation, so that's where the two delta H pluses go. Okay. So that would be the first product for chloromethyl cyclohexyl. cyclohexane. And then for this one, we would break that carbon-hydrogen bond. And again, the idea is to form the double bond. That's going to give us the double bond now inside the ring with the H plus. So what I'm doing here is, this is my alpha carbon. I have 3 beta carbons. I'm going to lose the hydrogen off the beta carbon and form each of the products. So in this case, I'm losing the hydrogen off of that beta carbon. The transition state then would be the breaking of that carbon-hydrogen bond and the forming of the double bond, with the hydrogen that's being lost delta positive and the carbon being also delta positive. Is everybody okay with me so far? Right. And everybody did that on their practice problems if they had this molecule. If you didn't have this molecule, then make it a CH with a CH3, or make it a CH2 with a CH3, because it's basically the same mechanism. So
if you had a CH2, CH3, would you take the hydrogen off of like that first carbon, not the second one?
Yes, because the first carbon is the beta carbon. So the next carbon over would be the gamma one. And let me come back to that, because you can't lose a hydrogen off a gamma carbon. Okay. All right, so everybody's okay to this point? What about the beta hydrogen down here? That's going to give you the same product as the one we just wrote. So we could do that, but we can do that, and we will. So now we could take the final beta hydrogen and say, let's lose that one, lose that beta hydrogen, and again we would form a double bond inside the ring. And in terms of our transition state, then again, breaking the CH bond dotted line, forming the double bond dotted line, hydrogen becoming delta plus, carbon becoming delta plus. So this would be called 1-methyl cyclohexene. The product that we just wrote would be 1-methyl cyclohexene, and this would be like, I think, methylene cyclohexane. But this one we don't know how to name. We'd have to go to the sheet. So it's different than the other two. So then, given these two products, let's call this one A and let's call this one B. Which of these two products would be the major product of the reaction? And we can vote. We ready? So, okay, here's your choices. A for A, B is the major product B, or C, they're the same. They would both be major. So those are your choices. A for A, B for B, and C if they were both major products. Okay? (27-2). B is the major product. Okay. So Why? I'm going to count the number of alkyl groups attached to the double bond. So in this case, this molecule just has 2 because there's 2 hydrogens on this side. This one has 1, 2, 3 carbons. And so this has 3 alkyl groups attached to the double bond. This one only has 2. E1 always forms the most stable alkene, which is the most substituted alkene. Okay. Everybody okay with that? Now, remember that in a mechanism, when you add up the mechanistic steps, you get to the overall reaction. So in this case, this H plus is going to combine with this Cl minus to make HCl. So the overall reaction that I might write here would be to take this methyl chlorocyclohexane and create the alkene plus HCl. So in other words, if I'm looking at this as an elimination reaction, what am I eliminating? I'm eliminating HCl. Where the H from what carbon? The beta carbon. So I would get an HCl out of this, and I would get that double bond. So the overall reaction has the HCl. Where did that come from? The H plus combining with the Cl minus. Isma.
Go over one more time how to count the alkyl groups.
So remember that the carbon has to have 4 things attached to it. And we can either count hydrogens or count carbons. If you count hydrogens, it's going to be 4 minus the number of hydrogens. So when we go back to this molecule, when we go back to the molecule up, when we go to that molecule, this one, then we could write this and say, you know, instead of a CH2, I could write it like this. So these are my 4 positions that I'm looking at. How many of them are hydrogens? 2. So 4 minus 2 means there's 2 alkyl groups. It's this C and that C that are the alkyl groups. So that's what makes that have just 2. If we go up here to this one, down here we've got 1, 2, 3, 4 things attached. One of them is a hydrogen, so in theory 4 minus 1 is 3. This carbon, and that carbon are the 3 carbons. So that's always how we count. And if the molecule is not written, like if it's written CH2, just expand the 2 hydrogens so that you know that there's 4 things attached. I'll show you in the next one because we'll have a CH with a CH3. We probably need to expand that to get that 1 hydrogen.
Why does the chlorine only show up in the overall reaction?
It shows
What I had written was like in each reaction I had in the first part, and the reactions I had a plus.
like this.
Yeah.
Yeah, so it's still there, but this is the mechanistic step. So when you get the overall reaction by adding up the mechanistic steps. And so when we add up the mechanistic steps, the carbocation disappears, and it's the alkene final product plus H plus Cl minus. And so the H plus Cl minus would combine together to make HCl. But you can write it either as minus H plus on the arrow or put the H plus on the product side. Same thing's true up here for the Cl. All right, so does that help you with the H plus? So that's where the H plus goes. Now, let's go back and talk about substitution. So what happens with the double bond is that the double bond likes to get electron density. The way you stabilize a carbon-carbon double bond is to push electron density into it. So every time we put an alkyl group on the double bond, that alkyl group, the hydrogens are slightly positive and the carbon is slightly negative because the carbon picks up the electron density from the hydrogen. Hydrogen's electronegativity is 2.1 and carbon is like 2.4, so that means carbon is slightly more electronegative than hydrogen. Normally we would consider that to be a covalent bond or a mostly covalent bond. But in this case, I'm going to take that little bit of non-covalency or slightly polar covalent bond. This carbon now has extra electron density. It can now push it into the double bond. That stabilizes the double bond. So the more alkyl groups that are attached to the double bond, the more I'm pushing electron density into it, the more stable it becomes. So therefore, the more substituted it is, the more stable it is. Okay. Now, it doesn't matter what the alkyl group is. The alkyl group could be methyl, ethyl, isopropyl, 100 carbon chain. We treat them all the same. So the maximum number of things that can be attached to the carbon-carbon double bond is 4. And if there are 4 alkyl groups, it doesn't matter whether it's 4 methyls, 4 ethyls, 4 isopropyls, they all push the electron density in the same. It's like a carbocation. A tertiary carbocation is the most stable, but 2 tertiary carbocations are the same stability, whether they have methyls or ethyls or 100 carbon chains on them. They're all going to be the same. So it's the idea that there is an alkyl group versus what specific alkyl group is there. Yeah.
How is the beta carbon able to push its
The beta carbon isn't doing that. The beta carbon up here is being lost as an H+. So what's happening is I'm breaking the carbon-hydrogen bond and taking this pair of electrons and giving it to this carbon to form the double bond, and then the H+ is leaving. The beta hydrogen is not really, what it's doing is it's giving up its electron. It's giving up its electron to that carbon. So let me write a mechanism that is not correct. Okay. That's our carbon-hydrogen. Oops. That's our carbon-hydrogen, beta carbon-hydrogen bond. Okay. The hydrogen says, I'm leaving as H+. Although maybe the carbon's telling the hydrogen to leave, and oh, by the way, leave your electron behind. Right? So get out of here. But I'm keeping your electron. That carbon can now take that pair of electrons and it can now donate it so that these 2 carbons are happy, because now what I'm doing is I'm now forming that carbon-carbon bond. So the H+ left, it didn't push electron density in, it just gave up its electron to the carbon.
I'm saying my question wrong. Like in the picture to the left.
This one.
Yeah. How is that carbon that has a partial negative charge able to push its partial negative charge to the carbon?
Through what are called inductive effects. So, no, that's a good question. When we're looking at polar covalent bonds, this carbon would be slightly positive and that carbon would be slightly negative, right? How did the bromine become slightly negative? It took electron density out of the carbon by what's called an inductive effect, because it's more electronegative. I mean, I could say that this carbon's pushing electron density through hyperconjugation, but gonna not do that. If you want to know what hyperconjugation is, you could look in the textbook, but all we have to understand is the idea that there is something called an inductive effect where if one, like this carbon doesn't like its extra delta minus charge, right? I mean, even though it's taking it from the hydrogen, it's not happy with it because it wants to be neutral. Carbon's not an electronegative element for the most part. So, I mean, that carbon's like, I don't need this delta minus charge, so I'll give it to the double bond. The double bond's like, great, I'll take as much as you got. I'll take as much of the delta minus charge as you want to give me because that makes me stable. And so the carbon does that. And then that makes the double bond more stable. And if there are other alkyl groups, the carbon's like, bring it on. I'll take yours, I'll take everybody's. And the carbon's like, okay, I'm happy because then I'm getting closer to 0. Now the hydrogens are kind of screwed in this because they stay delta plus. But they're used to being delta plus, I guess. This is giving atoms human characteristics. If it helps you understand it, great. It's not how science works, but who knows? Nobody's talked to a hydrogen to ask it its feelings. Does that kind of make more sense? So it's what we call an inductive effect. Anytime electronegativity or delta plus and delta minus charges are used to move electron density around, that's called an inductive effect. There's also what's called a resonance effect, whereas if I draw a resonance structure and my two resonance structures leave me with an atom with a charge on it, that's called resonance. That's a resonance effect. We'll get into this mostly next semester. Although Top Hat may get into it next week for all I know. But that's when we'll talk about it next semester. All right. So does that kind of make sense? Any questions?
I was just gonna say next when we do the second type of one.
Yes. Well, let's do the one with the other problem that we did. Let's write the products of that reaction, and then talk about the major product, and then the second type of E1 with the OH group. Okay. So I think I hit all the questions, right? Why does the CH3? Why does an alkyl group push in there? Oh, I didn't talk about why you can't do a gamma hydrogen. So let me do that. Okay, so if I have, let's say I have a CH2 with a CH3. So I'm going to write, that is now my gamma carbon. Why can you not push the electron density from the gamma carbon? Because I can only push electron density one carbon at a time. So this can only go here. Number one, my alpha carbon is still positive. So we can only move the electron pair one bond. If I made the mistake of doing that, I would still end up with a plus charge, but here's what I would end up with. I would end up with a CH2 double bonded to another CH2. What's wrong with that carbon? The problem with that carbon is it now has 5 bonds. So I can only lose the beta hydrogen and only push that electrons to this carbon simply because that carbon has 3 bonds, it wants a 4th bond. So we can only lose beta hydrogens. We can't lose gamma, we can't lose delta. We can only lose the beta ones because they're the ones that when I move that pair of electrons over here, it's going to take care of the double bond. It's going to form the double bond, take care of the carbocation. Everybody with me, sort of? Not sort of? We okay with that? If not, stop me or or send me more questions. Okay. One of the questions is about rearrangements, and I think we're going to skip. We're not going to do rearrangements right at the moment. If I wanted to do rearrangements, I would have started the class with that, and it would have taken the entire period. So we're going to do rearrangements after the exam. But another question is, can we go over how to figure out what the products would be, especially with E1? Okay, let's do this reaction and figure out what the products would be. So no mechanism. Let's do this problem with no mechanism. For those of you who say, but wait, I did the problem with a mechanism. Okay, I could go back here to this original problem, and I could make this the mechanism with CH2CH3 simply by putting converting this to CH2 and making that CH3. So I could do that with this mechanism. I already did it down here. I think I should get rid of that because that'll just cause a problem. But exact same mechanism that I just did, add an extra CH3 on it. I'm going to ask you in exams, though, I'm going to say write mechanisms, but then write products of the reaction. So if I said, hey, this is an E1 mechanism, write all the possible products of this reaction. So what am I going to do? I'm going to say alpha carbon, beta carbon, beta carbon, beta carbon. And so I'm going to lose an H off the beta carbon and a Cl off the alpha carbon. So I'm going to get HCl formed. And so then the question is, okay, let's do that for this molecule. So let's lose HCl for that hydrogen, for the beta hydrogen that's on top. I'm going to get a double bond here with a CH2CH3 there. Let's call this beta hydrogen A, product A. Okay? Let's call this, let me write out that hydrogen explicitly and say there's HB. So I'm going to lose the chlorine and HB. So what beta hydrogen or what beta carbon am I going to form the double bond to there? I'm going to form it to the CH3, and that's going to give me product B. So what I'm doing is I'm losing the H off the beta carbon, losing the halogen, and forming the double bond between that alpha and that beta carbon. Okay. Does everybody see that? So then my third product is going to be, now let's take alpha or beta hydrogen C, and now let's lose that beta hydrogen and the chlorine. That's going to put the double bond below with the CH2CH3, and that's going to give me product C. Okay. So if you want to write the product, do this. I want to write the product there, so I write it out. I say, well, okay, HCl, double bond. And there's my product. Now write the molecule with the next hydrogen, erase the HCl, put a double bond there. This is probably not kosher with all of the organic professors. I'm sure they would probably call this heresy to show you just how to erase stuff and write the product. Like I care. But that's another way of doing this. But do you see what we're doing? We're just losing the H and the Cl. And our mechanism is we lose the Cl first, then we lose the H plus. We lose the Cl to form the carbocation, and then we lose the H plus to form the double bond. In this case, all I'm doing is showing you how can I write the product without having to go through the mechanism. And there may be times when you have to go through a partial mechanism to remember what the product is. That's fine. I'm not asking for the mechanism. in this problem. I'm just saying, give me the three products. Give me the possible products and then tell me what the major product is. Alicia.
For each of the products, so we have to say like plus HCl.
Yeah, we could. We could very easily say that. If you don't say HCl, it's not something I'm going to take points off for. It's not something that I'm going to, because I'm mostly interested in the organic molecule as opposed to the other ones. But if you're a detail-oriented person that needs to see the HCl, then put it there. If it freaks you out not to put it there, put it there. Okay? So that would be the products of the reactions, but what I'm most interested in is the organic ones. Okay.
What would be the purpose in you asking for just the products and not the mechanisms?
Because mechanisms are hard to, or take a long time to draw, right? Do you want an entire exam of just mechanisms for every reaction? So what I do, if you look at the older exams, I mean, I'm pretty much set in my ways. I'll occasionally come up with a question and somebody go, where did you pull that out of? And I'm like, really? It's not that big of a stretch, that question, but I don't view things, I don't view it as a big change, but it's other people, it's like, oh my God, where did he get that from? It happens. But mechanisms first, then products, writing the products of the reactions, because you have to be able to do both. On any kind of standardized exam that you take, not that I'm teaching for that, but you have to be able to write both the product and the mechanism. We don't have a lot of time to write the mechanism for everything. Sometimes just a bit of a mechanism, though, is helpful in getting the product. Sometimes you're like, I have no idea what this reaction is. Okay, let's go back to basics. Tertiary halide. All right, let's break the carbon-chlorine bond and get a carbocation and see what that leads me to. So you'll see both. You'll see both. If you had the right mechanisms for all those problems, you're not finishing the test. So that's why I asked just for the answers, or just for the products. And that'll become more and more as we get more and more reactions under our belts. Okay. All right, so we got three products. Any the same? Which ones? A and C are the same product. Okay, they are the same product. Next question would be, given A and B, since we've eliminated C, which one is the major product? A and B, or, to not cause confusion, D means that both would be the major product of the reaction. So which one's the major product? A, B, or both? Both would be D. Just to not have to worry about what does C mean. Okay? I think your thumb has to be off the... Nope, there it is. If your hand's within the box, it doesn't read very well. Okay, whoa, we got 17. We have 17 A's, we've got 6 B's, and we've got 9 boths. So I think, you know what I think we need? I think we need a minute. Discuss. So discuss for a minute, and then maybe we'll revote.
Yeah, so it has 3.
Okay, are we ready to revote? All right, let's revote. Which one is the major product? A, B, or both of them, D? Okay, we've moved to 26 Ds with 5 A's and 2 B's. Okay, so we moved to D being the major product. Why did we do that? Why did you do that?
There's 3 alkyl attached to them, which would be
Okay. So how many alkyl groups attached to A? How many attached to B? Well, okay. I heard a 2. Let me just, because sometimes with the CH like that, what you should do is make the CH like that, and then maybe recount. So how many alkyl groups attached to that double bond? 3. So there's 3 here and 3 here. So what would that do with our rules then? Our rules would say they have the same number of alkyl groups, and so our rules would say that those two are both the major product. So both A and B would be the major product of this reaction. We would consider them to have equal stability because we're just counting groups. Now you might say, but the double bonds inside the ring and the double bonds outside the ring, which one is more stable? And the answer would be, I don't know. Except that last night I was curious about this myself. So as I'm grading homeworks, I have more computational power on my desk than I need. And so I use this program to do calculations to figure out which one of these two were more stable. And it turns out that the double bond outside the ring is stable, more stable, but only by 1 kilocalorie per mole. Now, energies, we have a hard time, even if you were a graduating senior chemistry major, if somebody said, will 4 kilocalories like warm a cup of coffee or will it blow the cup up? We have a hard time knowing about exactly what energies is, but 1 kilocalorie per mole is not much. So what we would actually have is we would have a mixture of those two products. So they both would be, as far as I'm concerned, the major product. They have nearly equal stability. If they were 10 kilocalories per mole different, that's a whole other story. That would be, this one is definitely the major product if it's not the only product that's formed. Okay. So when I say we can count the number of carbons and that's good enough, actually that's evidence that it is good enough. So we don't have to worry about double bonds inside, outside the ring. 3 alkyl groups each. They're both major products.
So, are they equally?
Probably not, because this one is a little bit more stable, but not enough that I would consider that to be, they're both going to be the major products. If I did, and I should have probably done the calculation on the one that we did before, there's going to be a significant difference between those two. Maybe I'll do that for Friday. Okay. So we're going to consider, our rule is just count the number of alkyl groups. Same number of alkyl groups, equal stability. That's going to be our rule. Okay. So probably the first vote through, it was like, well, the rule's not clear. The rule's clear. Count the number of alkyl groups. If they have the same, we're going to call them same stability. Now, I'm not going to quibble over one being 5% more than the other. Same thing would be true. A tertiary carbocation, 2 tertiary carbocations have equal stability. Doesn't matter what they're attached to. They're both tertiary. Okay. Okay. So this is how we would write the products directly without a mechanism. Although you could very easily, if you were stuck, say, let me lose the chlorine, I got a carbocation, now I'm going to lose each one of the hydrogens to give me the three products. Which ones are the same? Okay, same products, I don't have to worry about that, they're both the same. Which one's the major product? Count the number of alkyl groups. Yeah.
Why is the double bond on the outside?
Because form the double bond, I lost this beta hydrogen right here. I lost that beta hydrogen because there's two beta hydrogens inside the ring, or two beta carbons in the ring. There's a beta outside the ring as well. And as long as a beta carbon has a beta hydrogen, you can lose that beta hydrogen for another week. Any beta hydrogen, you can lose. I'll modify that next week. But not for E1, just for E2. For E2, there's a question about whether you can lose a hydrogen or not. But we'll get to that next Wednesday. A lot of time in between there and now. Okay, so we're not going to do rearrangements, but let's do the alcohol. So let me change the mechanism. Let me go back to the original CH3. Let's react this with H2SO4 and heat. And what would be different about this mechanism compared to the one with the chloride? So OH cannot leave on its own. It needs to be protonated. So that means the sulfuric acid is a source of H+. What would the first step in the mechanism be? Protonate the oxygen. So the H+ is going to protonate the oxygen, and that's going to give me an O with two H's and a positive charge. So when you have an alcohol and you're doing dehydration, the first step is to protonate the OH. Now, since this is a tertiary carbon that the water is attached to, I can form a stable carbocation. I'm going to break the carbon-oxygen bond, and I'm going to end up now with a C+ there, a CH3, plus the H2O that was lost. Okay. So water cannot leave like a halogen can. So to make the water leave, what do I need to do? I need to protonate it first. So this is an extra step in the E1 mechanism. Protonate the OH, make water, well, what's sometimes called an incipient water molecule, because it's about to leave. It leaves, I end up with a carbocation. How about the rest of the mechanism? It's exactly the same as what we did with the halide. So the only difference in the mechanisms between OH and halogen is I need to protonate the OH group first. And if I protonate the OH group first, then I make a water molecule, then it leaves. And then I'm going to lose my beta carbons one by one on my carbocation. Yes, so in other words, you would have to have the transition state here go partial bond to hydrogen with a delta positive and a delta positive. So that would be your transition state for that. And then over here, we would still have the transition state of being breaking the bond to the O, a delta positive on that O, and a delta positive on that carbon. So this would be a newer transition state that we haven't written yet. Although, Although that transition state we have written. Because that's the transition state when a water adds to a carbocation and you lose the H+. So again, for transition states, partial bonds to bonds being broken and made, and then put the delta charges in, and then you're good to go. Okay. All right, Friday is going to be review. So bring your questions or shoot your questions to me, or I will let you shoot questions to me during the review session. If not, we're going to awkwardly stare at each other for a few minutes, and then I'll make up some problems, but if you bring them, it would be better.
Are you gonna record the review session?
Am I going to, yes, I will record actually both review sessions so that if you want to see what went on in the morning, you can see what went on in the morning and the afternoon if you're not here.
Post those on Canvas?
I'll do like I do every lecture period, it'll go up online.
Okay.
So this one will be up, give or take a couple hours, and I'll have it in your folder.